Hey everyone, welcome to class today. There we go. We're going to be doing assignment 14. This is day 2 of solving our differential equations, and these are going to be initial condition problems. Okay, so let's start with just a little review of solving differential equations. Bell work, if you will. Will you please find dy dx is equal to 2x. Will you please solve this differential equation? Remember, if you don't show the separation of variables, you're not going to get any points on that exam for this question. So start with the separation of variables and go to town. Please pause the video. Okay, so I want to see this. And then when you separate the variables and have x's on one side and y's on the other, yeah, integrate. So the antiderivative of 1 is 1. And over here, the antiderivative is x squared. Don't forget the plus c. All right? There we go. Not such a big deal. Don't worry about it. What about this problem? Dy dx equals y. Please solve that one. Pause the video, give it a try. Okay, I'm going to do separation of variables first. I'm going to get this differential dx over here. I also have to get y back over here. This y is not on the same line as this dy. This is in the denominator. I'm really looking at this. I'm going to integrate both sides. And I'm going to say, whose derivative is this? Well, this is the derivative of ln of y. Yes, the absolute value bars are now very important. And over here, I have x plus c. Okay, what happens next? Well, next, we want to exponentiate. Notice how the c is up here with the x. The c is not here next to the e. So I've got absolute y equals e to the x plus c. Okay, we can go further with that. We know that when we're adding these powers together, we could have written it as two things that have the same base, and we're multiplying. When we're multiplying and the things have the same base, we can add the powers. Here is what College Board wants to see. Now, when we've got that plus minus, well, I want to get rid of that next. With e to the c, that's e to the x. This is the thing I wanted to define as something else, like plus or minus e to the c equals a. So y equals a times the x. Okay? Now, if this were an initial condition problem, like the ones we're going to talk about today, we would give you some kind of an initial condition at this point. You know, we would say, okay, dy dx equals y, and y of 0 equals 4. So now, I don't want to have a general solution. I want to plug in this x and this y and figure out that a is equal to 4. And so the particular solution is that. Here's my particular solution to this differential equation. There are an infinite number of solutions. Here they are. But we've been given information to help us find the specific solution. And that's our specific solution. Okay? Okay. How about this? How about y dx equals x over y? Please do that one. Hey, welcome back. You know, I really wish if more of you would actually do the practice. Because if you did practice, you get more comfortable with this stuff. Much more comfortable than you are. Those of you who have come for remediation, in particular, I want to say, you want to do the practice before you take the test. Because in college, it's not going to be a retake option. Let's integrate both sides. Y squared over 2 equals x squared over 2 plus c. Yeah, sure, you could have a plus c here. And you call that c sub 1 and c sub 2, and you move them all over onto one side, and you'd say, now I've got c sub 1 minus c sub 2. And so over here, why don't we just call that c? Right, so move this over here. Why don't we just call this c? And there we go. See, there's only one c to work with now. Yeah. So what next? Well, this isn't quite done, is it? Right? I mean, the problem is that usually when we solve a differential equation, we want to think about this in terms of y equals. And we're not quite there yet. A lot of students multiply everywhere by 2. Or we have y squared equals x squared plus 2c. And to solve for y, we take the square root. Plus minus square root x squared plus 2c. And that could work. That's a nice solution. If I had an initial condition, I could plug that value in. So, for example, 0, 4. So, y equals plus or minus square root 0 plus 2c. Oops, I'm supposed to put a 4 here. Let's square both sides. 16 equals 2c, and c equals 8. Okay, not done though until we plug that initial condition value for c back in. And we're going to have 2 times 8 or 16. Okay. This is not a semicircle, by the way. If we go this other direction with this problem, we're going to actually move this here and that there. X squared minus y squared equals negative 2c. This is actually not x squared plus y squared equals negative 2c. This would be a circle, and as long as c turned out to be a negative number, we wouldn't have any problems with a negative 2 here. But this is a circle. That's not a circle. That's a hyperbola. A hyperbola is like, instead of an ellipse, you cut that ellipse and you take these parts and you flip them. This makes this kind of hyperbola conic section. Chapter 10 in the pre-cal book is all about conic sections, so if you're interested, go read about those. But for us, I'd like to dig into solving some initial value problems. So here, we'll start with this up front, 6x squared plus 4x, and y of 2 equals 10. Okay, solve that initial condition problem. I think we know how to be able to do that now. Okay, so we do that separation of variables, and then we integrate. We get y, 2x to the third, plus 2x squared, don't forget the plus c. Let's plug in our 2 for x and our 10 for y. Two to the third is 8. 8 times 2 is 16. 2 squared is 4. 4 times 2 is 8. And so that's 24 plus c is 10. And I want to subtract 14 from both sides. It's going to give me, subtract 24 from both sides, giving me negative 14 for c. So that has to get plugged back in here. And there's my specific solution to this differential equation. Please do not box your answers. Please do not box your answers. Okay, how about this one? How about dp dt equals 10e to the t? And p of 0 is 25. Please solve that differential equation. Hey, welcome back. Did you separate the variables? Got to see the separation of variables. If you don't see the separation of variables, you've just lost 5 or 6 points. It doesn't matter what you do after this. Really, really, really. Really, if you skip this step, if you skip showing them that you're doing separation of variables, literally the reader stops reading that question and moves on to the next student. So you really need to show this separation of variables. Integrate both sides. P equals 10 to the t. That's right. This is someone's derivative. Whose derivative is this? It's this guy's derivative. A constant times a function. You know the derivative of e to the is e to the. And we're just going to take that derivative and multiply that by that same constant. Don't forget the plus c though. Okay? Okay. I plug in a 0 for t and a 25 for p. Wow, e to the 0 is 1. So if I subtract 10 from both sides, 15 equals c. So let's plug that value back in. And now we're done. An arrow might be useful here. Don't box your answers. All right, how about this one? How about knowing that v is negative 32t plus 100. And we know that s sub 0 equals 50. All right, now how does this help me? Well, I've got to remember from last semester that v is the same as dx dt. No, really, it is. We know velocity is the rate of change in position with respect to time. Right, so now I can do my separation of variables and have ds equals negative 32t plus 100 dt. And when I integrate both sides, I'm going to have s equals negative 16t squared plus 100t c. Let's plug in our initial condition. 50 equals negative 16, 0 squared plus 100 times 0 plus c. Or 50 equals negative 16 plus 100 plus c. So if I subtract 100, I have negative 50 plus 16 is negative 34. All right, so then what's my position equation? R s of t is going to be negative 16t squared plus 100t minus 34. Excellent. There we go. Okay. Yeah, this one. dy dx equals cosine x plus sin x, and we have the initial condition y of pi equals 1. Okay? Go to town. It shouldn't take you very long, really. And no, don't do it in your head. You'll make mistakes. Hey, welcome back. I want to see that separation of variables. I want to see you integrating. In fact, those of you who are really paranoid, that shows the separation of variables. But this really shows. The only purpose to that line was to show the separation of the variables. Here I get y. The antiderivative of this is this. The antiderivative of sine is negative cosine. And don't forget the plus c. We know when x equals pi, y equals 1. Sine of pi, what's the y value at pi? The y value at pi is 0. Cosine of pi is negative 1. Negative 1 times negative is positive 1. If I subtract 1 from both sides, it looks like c is just going to be 0 here. So there's our particular solution. Okay. Sometimes College Board wants to ask the same question, but they say show that y equals x plus sine x minus pi satisfies the differential equation dy dx equals 1 plus cosine x, given that y of pi equals 0. Now, really, this is their way of saying American kids don't know how to solve differential equations, so we're going to tell them what the answer is supposed to look like. And we just want them to show the work that gets us to that answer. But really, you could just say, solve the differential equation. But they're saying it in this way because a lot of students struggle with this. And, sometimes I understand why. But other times, no, I don't understand why. I don't think you're going to struggle with this. If anything, maybe you'll struggle with the directions. And really the directions are solve this differential equation, plug in the initial condition, and you should get this. So let's see what happens. We've done our separation of variables. We're integrating. Whose derivative is cosine? Sine's derivative is cosine. Let's plug in our initial condition. Sine of pi, yeah, that's 0. So c equals negative pi. Nice. And there we've shown that. C equals negative pi. And then, I know you feel like, yeah, that's enough. No. Keep going, c equals pi, or negative pi, plug that in there, and do show them that, in fact, you get back to the same thing, okay? Oh, watch out, by the way, there are students who put the pi in here and the 0 in here. The input is x, the output is y. Watch out for that. Okay, what do we have next? Word problems. Oh, good. A couple of word problems. Okay. So, cars going 80 feet per second. By the way, this is a change in position, and this is a change in time. And so, this is a velocity. All right? And just, for the sake of, because many of you are starting to drive cars and have a sense of this 80 feet per second is 50 miles an hour. Okay? The car brakes to a stop in 5 seconds. Okay, we were going 55 miles an hour, and in 5 seconds, we've stopped. Let's take a look at this graph. Okay, this is a velocity graph. We started at 80. And after 5 seconds, we're at 0. Constant, we're slowing down in a constant manner. So, what do I notice here? Well, I notice that this is linear, and I notice that would be a change in v's, or the slope here would be a change in v's over a change in t's. We'd be looking at dv dt, that change in velocity with respect to time, and that's acceleration. So the slope of this line, that's our acceleration in this situation. Because our slope is negative here, that's called deceleration. Okay? So we're decelerating at a constant rate. What is that rate? Well, we would have, in fact, that's the first question. Yeah, and it turns out the answer to the question, what's your acceleration, is that we're going to use 80 and 0 and 0 and 5 and end up with negative 80 over 5 or negative 16. Now think about the units. The units here, feet per second, right? That's feet per second. And the units here are seconds. So this is feet per second, and this is seconds. So we have feet per second over seconds, or as some of you prefer, because it's cool to say, feet per second squared. We know this is our acceleration. And look, it's constant. As long as we are, as long as we're pressing on that brake with the same amount of force for the whole 5 seconds, that's going to be us. Okay, there's acceleration. Great. What's the velocity function? Well, let's start with A, also known as dv dt, is negative 16. So if I do my separation of variables, and then if I integrate, I get v equals negative 16t plus c. Of course, I'm going to need an initial condition, and yes, I've been given an initial condition here. I'm told that at t equals 0, we're going 80 feet per second. That's my initial condition. So I got 80, got minus 16 times 0 plus c. Looks like 80 equals c. So now I've got a velocity function. I know my velocity is going to be negative 16t plus 80. Fabulous. Now in the third part of the question, they're saying, well, if this is velocity, what's position? And they'll tell me that s of 0 equals 0. Okay, so I've got another initial condition, and here, v is ds dt, right? If I only see this, I don't know how to do separation of variables. So I'm going to have to remember that velocity is a change in position with respect to time. So what am I going to have here? ds equals negative 16t plus 80 dt. And I'm going to integrate both sides. Antiderivative of 1 with respect to s is s. And over here, we have negative 8t squared plus 80t. Don't forget the plus c because you were going backwards. And we were given an initial condition here. We were told that s of 0 is 0. So if I plug a 0 in here and I plug a 0 in here, I can find c. 0 equals 0 plus 0 plus c. And I'm guessing that c is 0. So what's our position equation? Well, this is our position equation right here. Okay, it's similar to, but not the same as Newton's falling object because this isn't Newton's falling object. This is you driving a car and hitting the brakes and coming to a stop in 5 seconds. Great. So now we've got these functions, right? We've got that a is negative 16. We have that v is negative 16t plus 80. And we've got s is negative 8t squared plus 80t. So I've got all those. Let's see what else they ask. How far does the car travel while stopping? Okay, so how long did it take this car to stop? Remember from our velocity graph? Velocity went from 80 to 0 in 5 seconds. So I want to know, and this is feet per second, and this is seconds. I want to know how far this car traveled. Well, do you remember what we did? It wasn't that long ago. If I integrate velocity from 0 to 5, that's going to give me s of 5 minus s of 0. Well, we've got a couple ways of doing this then, don't we? We could integrate that function. And what's that going to look like? It's going to look like 0 to 5, negative 16t plus 80 dt. And I do the antiderivative there, and I'm going to have negative 8t squared plus 80t. from 0 to 5. But guess what? Isn't that the same as position? And I just need to plug 0 and 5 into position. Well, if I plug the 0 into position, I get 0. If I plug a 5 in here, what am I going to get? Well, 5 squared is 25. 25 times negative 8 is negative 200. And 5 times 80 is 400. So here's what we want you to know. The change in position, the displacement, from the time you hit the brakes to the time you come to a stop, going 55 miles an hour, is 200 feet. It's not one car length. It's gonna take you 200 feet. 200 feet? Guess what? That's 2/3 of a football field until you come to a stop. Please leave more than one car length in between you and the person in front of you. Because if they stop and you don't stop, you're going to go through them unless they're 200 feet ahead of you. Just be mindful. It takes a while to stop. And this doesn't even count the time it took the signal to go from your eyes, uh-oh, that's not going to work, is what your brain says a second later, and then you start hitting the brake. So really, drive safe out there, people. You're too important to me. Okay, now it's usually at this time that I would play for the students in the classroom the Apollo hammer feather drop. Okay, so I would encourage you to go watch that video. It's like 2 minutes. It's pretty cool. And don't say we didn't go to the moon, please. It's not funny. It really isn't funny. There really are people who believe that. But we did leave a car there. Yeah, there was a car. Just bring some batteries and we got a car. Okay. And so when you watch this video, it's pretty spectacular. And the way I want to talk about this is I kind of want to look and see if it seems reasonable. So let's take a look. On the moon, gravity due to acceleration is 1/6 of that on Earth, and so there's our acceleration. It looked like at time equal to 0, he wasn't throwing the objects, he was just letting go of the objects, so I'm going to say that at time equal to 0, velocity was 0. And how high did he drop it from? I don't know. How about we say he dropped it from about 4 feet high? At time equal to 0, height of the feather and height of the hammer was 4 feet. Okay, maybe it's a little less. I always think astronauts, they're pretty heroic, so they're going to be tall. Okay, so what do we have here then? Well, oh yeah, I wanted to build this S of t function so we could see if in fact the amount of time to hit the ground was the same. So this is the same as dv dt. So let's do our separation of variables. -16/3 dt equals dv. Integrate both sides. V is going to be -16/3 t plus c. Okay, I'll use my first initial condition. If I plug a 0 in there and a 0 in there, turns out that c is 0. Now, here's the thing. If you do this in your head, you're not showing the AP reader that you know how to use the initial condition. So please, even though you can do this in your head, please show using the initial condition so you can get that point, right? If I don't show them that I'm using the initial condition, they're not going to know I'm using the initial condition, and I should get that c equals 0. Okay? So now we know that velocity is -16/3 t. Cool. But velocity is also ds dt. -16 t over 3. So let's do separation of variables. And let's integrate. Okay, that's going to give me s equals -16 t, -8 plus c. Okay, and if we plug in a 0 for t and a 4 for s, 4 is negative 8 thirds 0 squared plus c. We get c equals 4, and so our position equation, s of t, negative 8t squared over 3 plus 4. Now, what was our question? Did that video look like a hoax? Well, let's see how much time it would take to get from our initial height, 4 feet, to the ground. So we set s equal to 0. And let's solve for t. All right, we're solving for t. I'm going to subtract 4. And really, I just want to say, please don't divide by this fraction. It makes you so upset. Why not just multiply by the reciprocal? See, look, they go away. Here we've got 12 over 8, which is 3 halves. Is t squared, take the square root. In this situation, negative time doesn't make any sense. I'm just going to leave it like this, square root of 1.5. Well, I know the square root of 1 is 1, and the square root of 4 is 2, and this is between the square root of 1 and the square root of 4. So this is just over 1 second. I could probably get it pretty decimally, and then I could do a little timer thing on while watching the video, and I could see that, if he's really dropping it from 4 feet, yeah, that's not an unreasonable amount of time then. Okay. So, we just did a problem on the moon. That was something that the early natural philosophers in the 1600s were really considering. They wanted to create a system of understanding the universe that didn't just work on Earth, but it worked everywhere. Everywhere. Wow. They're doing that in the 1600s. They're trying to describe all the things, falling object, not just here on Earth, but over there on the moon too. They're trying to create a system of understanding the universe. That's what this math starts out as. Or it starts out as Bernoulli is arguing with the wine merchant who provided wine for his wedding, and he argued with that wine merchant saying that they didn't drink the amount of wine that the wine merchant said. And what did he do? Well, he had to invent a whole new type of math to figure it out. And we'll be seeing that in a subsequent unit dealing with volumes. Kind of exciting. All right. Let's take this a step further. Oh yeah, Russian probe. Okay. This is the one I want to do because it came from an AP question. dy dx equals 3x squared over e to the 2y, and y of 0 equals 1/2. So the first thing they say is, the first thing they ask me to find here is y equals, or find f of x. We know that f of x equals y, and so we're looking for the solution to this differential equation. Okay, give it a try. It's AP worthy. I'll catch this swap blue while you do that. No, actually, I guess I can't because you're back. So here we go. We'll do separation of variables. E to the 2y dy equals 3x squared dx. And we integrate. Okay, so what's the antiderivative here? Well, I know that the derivative of e to the 2y is e to the 2y. But if I take the derivative of this, I get e to the 2y, but don't I also have a 2? But there's no 2 here. So there must have been something present on the original function, so that when I took the derivative of that inside and the 2 came down, they canceled. And then over here we've got x to the 3rd plus c. Great, let's use our initial condition. I'm plugging in a 1/2 for y. 1/2 times 2 is 1. So we have e over 2 equals we're plugging a 0 in here. 0 plus c. So c is e to the 2. Nice. Okay. So then I can write y. I'm going to write e to the 2y over 2 equals x to the third plus e over 2. Nice. But we're not solved for y equals yet. And remember, that's what they wanted. They wanted us to find y equals. Okay, so let's multiply everywhere by 2. E to the 2y equals 2x to the third plus e. And now what? No, I don't take the square root. I take the ln of both sides. And this is going to come down. So 2y ln of e equals ln of, yeah, so that's going to spit out some negative numbers. So I better do this. And yes, that really is important. And don't forget I was going to say don't forget the plus e, but didn't we find that already? Yes, we did. Okay. ln of e is 1, so I still need to divide by 2. So there's my specific solution. Okay. Now, second part, they give us, second problem. Okay. Part B. Find f of x given that dy dx equals 3x squared plus 1 over 2y. And one more thing, f of 1 equals 4. Okay, so first find that, and then they say, and then find f of 1.2. Okay? All right, so separation of variables, 2y equals 3x squared plus 1 dx. Integrate, we're going to get y squared equals x to the third plus x plus c. I like using my initial condition now. 16 equals 1 plus 1 plus c. So c is going to be 14. Okay. So now we've got y squared equals x to the third plus x plus 14. But we don't want y squared. We want y equals. So let's take the square root of both sides. Okay. I take the square root. I take the square root. I get y equals. I know you're saying that, so let's confront that. X plus 14. Okay, so how can I know whether it's the positive version or the negative version? I mean, maybe the answer is it's both, because look, y squared, it's got that y on the top, it's got that y on the bottom for each of those x values. Yep, no, I don't think I can. If I just saved plugging in the ordered pair for now, I would be plugging in. This would be a C. This would still be y over here. I'd be plugging in 1 plus 1 plus C, 2 plus C. Let's have to square, but no, that has to be there. Okay. There's our solution. And oh, look, they wanted me to find f of 1.2. Yeah, not without a calculator, I'm not, because I'm taking 1.2 and cubing it. Sorry. No, not without calculator. So, 1.2 to the third plus 1.2 plus 14. Let's try that again. 1.2 to the third. Good. Plus 1.2. Yes. Plus 14. Good. And don't forget the plus and minus. And so we get that f of 1.2, 2, comma, 16.928. But we also get 1.2 negative 16.928. Okay, 2 places. All right. Now, what about this one? Yeah, this one. f of x has an inflection point at 1, -1. And the slope on f at that point, 1, -1, is -1. If f double prime is 6x minus 6, find f of x. Okay? So, what do we need to do? Well, I think what we need to do is we need to recognize that this is the second derivative. And if I integrate the second derivative, I'm going to have y prime equals 3x squared minus 6x. Now, what do we know? Well, we know that the slope of f, that's called f prime. F prime is -1 when x equals 1. F prime is -1 when x equals 1. Well, oh yeah, because when I went backwards, I was supposed to have a constant. So plus c. So we get -1 equals 3 minus 6. It looks like c is positive 2. So let's replace this with a 2 and say, great. Isn't that great? But we were asked to find the function. So let's integrate again. And what do we know? Well, I know that there's an, I'm looking at this thinking it's something to do with the second derivative because there's an inflection point on f there. But really, that's an x value, and that's a y value. And what is it that I need right now to find c? I need an x value, and I need a y value. So -1 equals 1 to the third, minus 2 times 1, plus 2 times 1, plus c. So that's 3 minus 3 is 0, so c is -1. Ta-da! There's our equation. You might want to watch this one again because it wasn't hard, but it is really sort of surprising. Okay? All right, last problem I think I want to look at with you today is actually another sort of true life stories. This is the Russians sent a probe to Mars a few years back. You can certainly look this up on the internet. And the Russians have always had a very special relationship with the French. There's a lot of French in Russian language. The word, this word, you heard that word? Bistro? Yeah, that actually is something coming the other direction. It's from the Russians coming to France and sitting down and saying, quickly, we want the food quickly. Bystra. Bystra in Russian, по-русски, is quickly. And so, yeah. But usually things go in the other direction, or did for a few hundred years. Peter the Great was very enamored by the French. Catherine the Great brought European ideas from Germany into Russia. But really, this metric thing, yeah, the Russians are doing it. How come we can't? So let's solve this differential equation. And I will tell you what happened with the Russians and their trip to Mars. ds dt equals 0 at t equal to 0. And originally, this probe was, when it entered the atmosphere, at 60,000 meters. So that's my s value at time equal to 0. Okay. So we'll do some separating of variables, and we'll get ds dt equals negative 3.71 t plus c. Okay? So let's plug in our initial condition. Remember that velocity at 0 was 0. So I put a 0 here, and I put a 0 here, and I get that c equals 0. Cool. So that goes away. We'll integrate a second time. dt. And now I get that s equals negative 3.71 t squared plus c. And again, we put in our second piece of information, that time equal to 0 when the probe entered the atmosphere. It was at an altitude of 60,000 meters. So if I plug a 0 in there, and a 60,000 over here, I'm going to see that c is 60,000. Great. So now we can write a position equation. Our s of t equals negative 3.71 t squared plus 60,000. And yes, this is with calculator. Mohammed, you know that because you see that decimal there. Okay, great. Now, the question is, how long? So what was supposed to happen was that this probe was supposed to enter Mars's atmosphere, and then, do its descent cycle. But because one of the engineers, when they were typing in the long string of numbers, they were off by one digit. Instead of landing on the surface of Mars, this seems to have crashed into the surface of Mars because just because. So what I'd like to do is use this position equation to find out how long it takes for position to equal 0. Okay, so we're solving this equation. Negative 3.71 t squared plus 60,000, and I'll subtract 60,000 is negative 3.71 t squared, and yes, I'm going to divide by 3.71, negative 3.71, and we subtracted that. So negative divided by negative is positive, that's fabulous, and I still need to take the square root. So let's take the square root of that. Okay, so we've got 60,000 divided by 3.71, and we wanted to take the square root of that number, and I get 127.171 seconds. So it's going to take that long for this object to hit the ground, to have a height of 0. Great. Now, the question I really wanted to ask is, it took a little more than 2 minutes for this thing to fall. What I really want to know is, how fast was it going when it impacted on Mars? Because it wasn't a gentle landing. Well, we had a velocity equation, remember? It was just negative 3.71 t. And if we plug in that value, v of 127.171 is going to be negative 3.71 times that, so times negative 3.71. And we seem to be going, if we are this poor little probe, 805. And what are the units here? Oh, buddy, this is meters per second. Now, think about it. A meter is 3 feet. And so this is like 1,400 feet, 1,500 feet in 1 second. 1,500 feet, 5 football fields, 1 second. It was a big impact on the surface of Mars. This poor little satellite. Yeah. So be very careful with your digits. And behold, you know how to solve differential equations now. I think that's really cool. Okay. So I'll see you in our next video, and I hope you have a fabulous day.